to another video, guys. That's all about stationary points. This question 1, exam styles questions, and it seemed to me really hard in terms of like if you go a normal way according to the theoretical basis how to explore function on the stationary points. So that's why I decided to clarify the case, how you can save your time on exams and maybe just go a little bit way around. Let's get started. Here's the question. Pause the video, try to do by your own. Okay, so I'll clarify a few details here. You need to find all stationary points, means any single one, and classify them. It means you need to state whether it's maximum, minimum, or it is a point of inflection. The function looks like two radicals that you subtract, but maximum power is x to the power 4 and h1. There are a few questions. First of all, let's set up a domain for this function. How to set up a domain? What you can do, you can start plugging the values, or you just simply can use GDC, because obviously you need to prove your workings. It's not enough just to build a graph and just click on the maximum point, click on the minimum point, yes, and on your calculator, and that's how you can find easily. No, you need to prove your workings. But to prove, what's the domain, you just need to plot the graph from negative infinity to positive infinity and say what sort of behavior the graph shows, okay? So that means if you do that, there are no limitations for x. That means domain is all real numbers, okay? So that's done. The next step, how to explore, you need to take derivative. So you take in df dx, you differentiate with respect to x, okay, your function, and find a derivative. And as you know, at stationary points, you need to equate to 0, all right? So what we're gonna do, we taken the derivative of the compound function. Let's have a look. Let's say this is f1, the first radical, and this is f2, the second radical. So f1 from x simply represent the compound function because it's square root of just another function g1 from x, where g1 is actually becomes polynomial of power 4 from x, okay? So normally, right now, you understand that this is f prime from x is equal to simply you differentiate f1 prime, okay, from x, and you add the second function prime from x. So what about the second function? The second function looks absolutely the same. It's square root of g2 from x, okay, and this internal function under the square root is polynomial of power 4 from x, okay? So what we're going to do right now, we're going to do the following. f1 prime from x will look like the following. Is 1 over 2 g1 prime from x and 1 over square root of g1 from x, according to the rule of differentiations. So we use the compound rule and chain rule here. So what about the second one, f2 prime from x? We'll have the same structure as 1 over 2 g2 prime from x and 1 over square root of g2 from x. So that's how it looks like. Okay, so what we're going to do right now, we just need to state the general derivative for each g function. So g1 prime from x is going to be equal to, we differentiate what we have under the square root in the first radical. It's going to be 4x minus 6x and minus 6. Okay, so what about the second one? g2 prime for the second one is going to be 4x, sorry, my bad, x cubed, of course, 4x cubed minus 2x, okay? And if we plug back, we'll get the following complete structure for both derivative. Let's move there and let's plug in back. and say that f prime from x is going to be equal g first prime is 4x cubed minus 6x minus 6 over 2 square root of what you have initially, x to the power 4 minus 3x squared minus 6x plus 13, okay? Plus 13. And we need to add the second derivative that we got before. So the second derivative is going to be equal 4x cubed minus 2x, okay? And we divide by 2 square root of x to the power 4 minus x squared plus 1. Because there are no limits for our x functions, so in the bottom part as well, it means from negative infinity to positive infinity, we need to equate to 0, and we also need to make sure that under the square root equation expression is not going to be turned onto 0 expressions, because you are not possible to divide by 0, okay? Now we need to solve this equation, because we need to equate to 0, as you can see there, and we need to solve for x. That's how we find stationary points. Which way you can use? Of course, you can use again your GDC. So using GDC, you can find out solution for f prime. But I want to notice that there is no any limits for f prime. So it means f prime function defined everywhere for every single x. So the main is for x from negative infinity to infinity, means x from real numbers. Okay, now we go to equation solver into GDC and just normally solve that. That means we've got the following solution. The equation solver will deliver us two solutions as 1 over 6, 1 minus square root of 37, that's the first x1, okay, and x2, so we can also calculate it. I already did it. It's around negative 0.847. And x2, there is another solution, which is around 279. 2.79, let's say around 2 decimal place, 75, okay? We've got stationary points. And now we need to provide the further research about stationary points. So we need actually to estimate what we have at those points for our function, whether it's maximum, minimum, or it's just the point of inflection. So that's why what we're gonna do right now, I just want to build the table where we put x, we put the value for fx, and amongst the values, what I'm going to do, I'm going to list all possible values, including the endpoints, which is negative infinity and positive infinity. We need to understand the general behavior of our function fx. So that's why I first start from negative infinity and positive infinity. I would like to explore on endpoints, or probably I'll just list them on in increasing order, okay? So negative infinity, then x1, which is 1 over 6, and 1 minus square root of 37, or if you like, you can use decimal format, no matter. Then 279, and then positive infinity. Okay, so the first reasonable question, you need to understand what will happen with fx when your x tends to negative infinity and when x tends to positive infinity, okay? So the question is to which value fx tends to. It might increase to infinity, it means it can be rising up to infinite number, or it can be decreasing. There is no idea. Of course, you can use again your GDC and just see what's happening on a larger scale, what's going on with your function. If x is a very big number, and big positive number and big negative number. Okay, so for example, how I offer you, if you have no case, if you have no idea how it works, like for, without using GDC, how you can at least estimate. You can plug big, very big numbers and see what's happening with the fx. There definitely should be some asymptotic behavior, or if it's not asymptotic, you definitely understand that it will go to infinite numbers, infinite big, or infinite like negative numbers. Okay, so that's why what we can do the following. So we can take first x tends to negative infinity. It means that we can list the value for x as the following. Calculate the corresponding f value using like normal calculations. Okay, I will start from negative 100, then every time increase by multiplying by 10, so that means it's going to be negative 7, next negative 10,000, 10 to the power 4, and so on. And let's calculate, let's plug those values using calculator into your original function instead of the argument. Okay, so that means I'll get the value negative 0.9695, that what my calculator gives me. Here is going to be negative 0.99, okay, and 7. So you see that it's increasing but very slowly, while x argument increasing by a pretty huge amount, 10 times more. Okay, what about negative 10,000? It's around 0.9997. So that means if you finally plug the really big number, you skip this chain, you understand that the final asymptotic behavior will be close to negative 1, all right? So that means this is the target. You can say that when x close to negative infinity, fx becomes negative 1. It tends to negative 1. So that's why y equals negative 1 becomes the asymptote. So this is an asymptote for your function. Asymptote. So that means it's not definitely neither maximum, neither minimum. Okay, it's not the stationary points, and obviously that's not the case. You just define the general behavior. Okay, so let's explore what's happening with x when x is very big number. Let's say it's very close to positive infinity. You do the same trick, you plug in the numbers 100, then 10 to the power 3, 10 to the power 4, and finally skip, you plug infinity, like absolute number. Okay, so if you plug again into your original function, here first you'll get 1.039, okay, round. So next, 10 cube, that's going to be minus 1.003. If you plug 10 to the power 4, you'll get negative 1.003. Okay, so you understand that finally you'll approach to negative 1. Okay, so that means here is also asymptotic behavior when x tends to positive infinity. Okay, so we've got that, and we need to define the rest part. What stays for x equals 1 over 6, 1 minus square root 37, and for this. Okay, so what you can do in that case, by the way, you can also explore the concepts of limits. So I'll show you maybe an alternative way if you want to prove that without just playing with a limited case of numbers. So you can explore just simply the limit when x tends to positive infinity of your function fx. So what I recommend to do, so either positive or negative infinity, what I recommend to do if you start exploring that in normal way using the limit concept. You have, let's say, two radicals. let it be radical 1, okay, and minus radical 2. What I recommend to do, I recommend to multiply the top and the bottom part by conjugated. So it means you have this structure, so you multiply by square root of r1 plus square root of r2, okay, and you divide it by the same expression. So that will help you to cope with the limit, okay? So that's an alternative case, how to explore the asymptotic behavior. Asymptotic, okay, behavior. Okay, so now we need to explore the points x corresponding to 1/6, 1 minus square root 37, and 2.79. We need to provide first exploration, whether maximum, minimum, local minimum, or the point of inflection. So instead of using the normal way of how we can do that, so I just show you the sketch of the graph and offer another way around. Instead of finding the second derivative, yes, and trying to explore like the second derivative f prime, f2 prime from x more than 0, so in this case we'll have local minimum, or vice versa, a second derivative less than 0, right? It's going to be a local maximum. I'm not going to do it this way because it's definitely be difficult, and in case you need to take the second derivative, you need to plug the values around. So I don't want to do that. Instead, I'll offer another way around. Let's see, this is already the sketch of the function f from x, okay? And you clearly see those 2 points. So the first point is 1/6 minus square root of 37, which is the value around. So let me see, this is the value. Oops, let's take another color one. Okay, so I just mark the points for x. So this is 2.79, and as we calculated, this is another value. So this is x2, and this is x1. This is the value negative 0.84, as we calculated before, right? We estimated that. Okay, so let's move there. And what I offer to you, what if you calculate, what if you plug the value for the f prime from x nearby the first x1, so around x1. So means you can have a little step to the right, and let's say calculate the f prime from x that you already calculate in general way at this point, and also you can calculate f prime from x there. Okay, so what it means that technically you're trying to calculate the gradients a little from a little to the left from their stationary points, and it definitely should be positive, right? And here, for example, which is going to be a negative. So it means if you calculate values for f prime x around the point, around the stationary points, and if you establish that f prime on the left part is negative, it should be negative, and f prime around but a little on the right from your extreme point, from your stationary point, and it's going to be positive, you'll have the maximum, okay, according to what I've already prepared for you. So that's the strategy. The same way you can calculate f prime here, a bit away from 279, a bit smaller and a bit bigger. You can also calculate that and figure out that here this f prime should be negative, okay, and this f prime is supposed to be positive. In this case, you'll get the minimum value. So this is local minimum. I'm not going to do that. You can also play with fx value. I'll just show you another way. Instead of like calculating derivative f prime, you can also just calculate the function value around. I'll show you just for, let's say, the first value x1. So you have x, you have fx, and you have the minimum, sorry, the maximum point for x, negative 0.84. So you calculated their value exactly in this point, and it will be 3.162, okay? So as we already proved, this is maximum. But what if you didn't know? So what you can do, you can take a little step below and say, okay, let it be negative, let me see, around, just let me calculate quick. For example, you calculating at the point and say minus. Yeah, that works. So you can calculate at the point, let's say negative 1. So just around 0.15 away from your point. And you can calculate at the point, let's say even 0 if you like. So if you plug 0, you'll get 13 square root of 30 minus 1, which is definitely is going to be lower than this maximum value. And here is the value is going to be lower, okay? So lower than the maximum value, and here is going to be lower as well. So that's definitely you establish the value as the maximum point, okay? So that's how you can play with values instead of like going in classical way, okay? Or just using GDC to clearly state that, okay, this is maximum, this is minimum. But for the complete exploration, you need to prove somehow. Okay, so, and we've got the first maximum value corresponding to one stationary point, and in the same way we can explore another point which is 279, and we can also just estimate in the same way that this is the minimum value, and if we plug the value in, we'll get negative 1.5, negative 1.54 and 7, which is the local minimum, okay? So that's the local minimum, and here is the sketch of the graph where you can clearly see that we explored completely. We also explore asymptotic behavior because in that way round it tends to negative 1. On a larger scale on your calculator you definitely see that, but we also estimate without any like graphing tool, okay? So negative 1 and negative 1 here. That's definitely asymptotic behavior. And clearly see the maximum and the minimum. Hope you like that. That was complete exploration of the function. It seems to me that it's really hard question for A-level. But guys, now you have the tool how to estimate, how to approach this problem. If you have no idea, if you're not allowed to use your GDC, the way is what I show you in this video. Thank you guys, and don't forget to check A-level zillions classes. And don't forget to check my videos dedicated to A-level stuff. That was Daniel Dallas. Peace out.